Formal charge where?
On the oxygen.
How would I stabilize that?
The house over 7.
I could protonate it. Okay, what could I protonate it with?
HCl.
We could run the suggestion of the HCl. Unfortunately, the HCl is actually going to stay out of the picture for a very, very long time. So much so, I'm just going to erase it. It's actually going to be our solvent, our ethanol. That can deprotonate. And we could potentially end with what was shown as our final structure. Because we don't care about stereochemistry, we can do that rotation and not really freak out. Yeah? Okay, and we might say, cool, there it is, we're done. But remember, we've got weird results coming out. Okay, so what I want you to think about would be, what is reactive in this solution? What is the most reactive thing floating around? Right now, at this point. We still have the ethoxide. We still have a strong base in solution. If we have a strong base, what should we be worried about? I know where you're going. If we have a base, we should consider an acid-base reaction. It could be as simple as just removing an acid or neutralizing an acid. But where else do we see acid-base reactions show up? Elimination reactions. Okay? So if we look at that structure, is there an acidic hydrogen? And if so, where? Where? The alcohols are absolutely acidic. Okay? But all that's going to do is kind of take us backwards and not really do anything different, which would suggest not a big deal.
Alpha carbon.
Alpha carbon? What do you mean?
So strong base attacks hydrogen alpha carbon.
You mean this blue hydrogen? Why is that blue hydrogen acidic?
Because the
The base comes in and removes that hydrogen.
yeah.
The resulting structure would be a negative carbon. And you're telling me a negative carbon is remotely stable.
So elimination is hydroxide leaving.
Hydroxide's a bad leaving group, so I don't accept that as an answer to explain why that negative carbon is allowed to form.
Because the hydroxide, the anion, is dissolved as a solvent. And always
You're still addressing the hydroxide. I'm not asking about the hydroxide. I'm asking about that carbon. Why is that carbon, that negative carbon, allowed to form? Because even to get the hydroxide, you're asking about doing another step. Yes, but first we have to prove that that structure is a valid structure to draw. Why is that negative carbon allowed to form?
This resonance.
There's a resonance stabilization within that structure. That resonance is explaining why, that hydrogen is acidic. Okay. That is the important thing to address there.
the only one.
Okay. That hydrogen is, in this structure, the only acidic hydrogen, or the most acidic hydrogen. There are the hydrogens on the alcohols. Those aren't going to lead anywhere productive. Like nothing can happen from those. The alpha hydrogen, there's only one alpha hydrogen in this structure, so we're kind of stuck there. Okay. We might just say, wouldn't that just as easily return backwards? Couldn't those electrons just go right back and go back out to pick up H+? Yes. Okay. They could. Okay, but what Lee is suggesting is that they could also do something else. What were you suggesting now, Lee? Now that we know that structure was allowed to form, where could those electrons also go?
So make a pi bar and hydroxide, yes. group. Size chart. It's alkene.
We're going to address that in a second. Does everybody see that? Okay. So now, is it possible? So you don't know. You're just like, I think something can happen, I'm going to do it. You were just playing with it? Okay, that's cool. Is hydroxide a good leaving group? No. But what is it leaving into? Into a hydroxide environment. So the leaving group, as far as the stability of the overall solution, is effectively neutral. Okay? So at best, that should then say that this is an equilibrium that would go backwards and forwards. Okay?
The stable, the conjugate pi bond. That's why the driving force
There is a driving force here. What is the driving force to do this?
pi bond to pi, conjugate pi bond.
This structure, we have the phenyl ring followed by sp2, 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 sp2. This structure has massive conjugation. What does that do for us? That drops the energy of that structure, meaning it is now an actually pretty stable structure. Okay? So that conjugation was a very good thing to do to eliminate that, because we do get a more stable product out of it. So we typically only evaluate the leaving group and ignore the other half. In this case, we have to evaluate the other half of our structure. The other half of our structure is what's driving this. That structure has become more stable than even the hydroxide is a bad leaving group. Okay? So awesome. So before we move to David, is that where you stopped?
Very stuff.
That's where you stopped? Okay. What do you see, David? What functional group is now highlighted in green? Green was probably the wrong color. Can you see that? Is that okay? Ish? Let's make it orange. What functional group is highlighted in orange? That is an enol. Are enols stable? No. There's a reason when we talk about enols, it's keto-enol, because the keto form is more stable. What happens? We do a keto-enol tautomerization. Okay. I'll let you cheat for your mechanism and just say that it happens in 2 steps, because it does. And we'll address why we've got to do it in 2 steps here in just a second. Whoops. Here, here. This side's fine, that side's fine. There's our ketone. There's a hydrogen. It happens in 2 steps. We're changing the location of the hydrogen. Instead of being attached to the oxygen, it's attached to the carbon. These are not resonance structures because you've changed the location of an atom. The formulas are identical, though, and so they are very commonly tested as, is this resonance? This is not resonance because you've changed the location of an atom. Why does it have to happen in 2 steps? That hydrogen cannot jump from the oxygen to the carbon in a single step. Why not? That's a really hard question.
It's leaving in the hydride, right?
Nope, still leaving as H+.
You can't do a form of the ring.
Okay. It's the size of the ring structure that would have to form to allow that to happen. So what will happen is step 1 is a base comes in, removes the hydrogen, shuttles the electrons. That would be a step 1. The step 2 is those electrons come out and react with hydrogen in solution. Okay? It is a solvent-mediated reaction happening in 2 steps. Okay? So now we might say, hallelujah, we're done. Right? Because that looks reasonable. We don't have the same conjugation, but at least all the things are there, right?
Don't you have some acidic hydrogens again?
We still do have some acidic hydrogens, okay? And we could potentially try to enolize those, okay? I would highly recommend that you play with those and see where it goes, okay? What you will find is it goes nowhere, Okay. You will end up forming a nucleophilic carbon. You're in a basic environment, which means you're surrounded by other nucleophiles. Okay. So yes, that is a valid pathway, but that orange hydrogen that you're now referencing as potentially acidic, yes, it is acidic. It's not going to take you anywhere useful. Okay.
I was doing my counting wrong. Basic math error.
Okay. Does anybody see anything potentially interesting with this that might be like, that's a little weird? I don't really like those things near each other. You don't like the ketones near each other? Why not? You don't know. Okay.
The two carbonic carbon is positive.
Maybe if we draw out a resonance structure, and in fact, I'm going to draw out two simultaneously. I'm going to look at both of these resonances at the same time. We might draw attention to why we don't like the concept of two carbonyls next to each other. What is the issue with two carbonyls next to each other? We have two positive charges right next to each other. That is an incredibly unstable system. Okay? That's not happy. Okay? How could we potentially stabilize that situation? Okay, so we have a massive centralization of positive charge. Okay? If we've got a bunch of positive charge piling up, what might we want to add to this? Some what? HCl is going to supply what? More positive. Okay? So that's probably not a good idea to bring in at this stage. On top of which, what is the acid going to do? I mean, there's already a bunch of positive there. None of those are particularly reactive. What might we need to help stabilize a massive pileup of positive charge? H3O plus is still positive. There's a nice general answer over there. Was that you, Rob?
Yeah.
What'd you say? We might want some electrons. Where the hell can I get electrons? What's that? Doing an elimination would potentially work. That gets us to an enol, which you're welcome to move that path, but it's going to be a dead end. Where else could we get electrons?
Don't you have a boatload of base in the solution?
Don't we have a boatload of sodium hydroxide in solution with a negative charge? Yeah. Yeah, we do. Okay. That hydroxide is going to somehow interact with that green structure to set off a cascade of nastiness. Okay. That nastiness is hinted at in your quiz. Okay. So it may be a good idea to take notes as you're doing the quiz. Okay, so I will allow you to use notes on the quiz so that way you can actually take notes, because there's a pretty big hint about what's going to happen with this that will help you figure this out. Okay. The other thing I'll do is a subtle manipulation of the structure. Whoops. Hopefully subtle. I don't screw it up too badly. Subtle manipulation of the structure. I just did a rotation about our bond. Okay. That's to set up some alignment of things that you might be like, well, what the hell are you doing? That's quite all right. Okay. But what I can tell you for sure is that within this box, your final answer becomes apparent. Okay? So what's going to happen is we'll get into lab, we'll run the experiment today. all the stuff that you guys just helped me walk through was fantastic. That was really, really, really good. And yeah, it's a boatload of crap. But it all kind of centers on that enol chemistry. That enol chemistry is a huge part of Chapter 10. It's a huge part of the next unit and the next unit. Okay? And if you got to take biochem, it's virtually all a biochem. Sorry, Milana first.
Why does it have to be something negative? Why not like positive to grab the hydrogen?
Well, the reason why it needs to be negative is what makes this unstable is we put two positives near each other. Okay? These negatives aren't all that close to each other, and if I brought in something positive to stabilize that negative, does that fix the double positive issue? It doesn't. In fact, if anything, it would maximize the positive issue. Okay? I don't like those two positives next to each other. Okay? That's what makes the structure very, very, very reactive. Okay? So, I'll say it again. Within the red box has all of the pieces of your final product. Okay? Remember, we did have that HCl. We haven't even addressed the role of HCl yet. Okay? So when you run your IR, okay, the IR is going to give you some hints about what bonds show up. You need to use that information and what's in that red box to predict a product to be like, oh, that's what happened. Your introduction is now going to be, this is what I'm trying to do. Not that I set out to stop with this black product, because I didn't set out to do that now, because that never formed. Your introduction is now, I set out to form whatever you're going to discover to be the end result today. Does that make sense? Okay. What do you got, Lee?
It's okay. The oxygen, the anion attack the carbon cation. So the
Like this?
yes. No, the opposite.
To do this.
Yes. Okay.
Let's just say no. Okay. That could explain some of your loss in yield, something like that happening. But at best, you would only get one doing that. You'd still have a positive charge at that other position. You'd have to neutralize that somehow, and that's not going to be easy to fix. So yeah, we don't see a lot of that happening.
Can you discuss how the OH is going to affect? Like, what is the negative?
What is that hydroxide going to do? Well, what was the problem with our green structure? What did we say? This is an issue we need to fix. Two positive charges. That hydroxide is what? A negative charge. How could that negative charge stabilize positive charge? Potentially donate electrons in. I'm not drawing the arrows because you need to figure out some part of this. Okay. Once you have a final answer, we can then open up and discuss a little bit more about what's in that red box, but you need an IR first for me to open that up. Okay. What the IR should do is help you know what should be happening in there. All of the pieces are there. It's now just a question of how you arrange those pieces and how it's going to go through.